go from the current slide. Now, I think I've gone over the announcements. You know, coming up in a couple of weeks is the college transfer days, fair days, and that will be Wednesday the 12th on the Birmingham West Campus, 9:30 to 11:30, and then on this campus, Thursday the 13th from 9:30 to 11:30. You can see this, anything you want to see from it. And the thing about the research program for especially pre-engineers, they have a great program, National Science Foundation sponsored, fantastic program. If you want to look at it, you certainly can. The deadline for that is coming up on the 15th of February. Okay. Asia, right? Okay. Now, I guess before we get started today in the class, and this probably will take more time than it should, but let me go over what today's going to be like. It's strange. I'm sorry about it. I'm going to go until 1:45. It's less than 30 minutes now. And at 1:45, I've got to leave. That's why my coat and everything's here, which reminds me I need two other things. That if I didn't do it now, I'm going to forget it. So, sorry about this. What's that? Oh, yeah, it must be. I thought I heard something fall, but it's probably my phone. Okay. Thank you for seeing it. Yes.
Could I get a copy of the last week past Thursday lab?
Sure. Okay. Anyone else need that? Okay. Yuck. I can't see. I'm going by feel here. Here we go. Okay. Now, a little bit about the lab. If you've listened on YouTube, you probably have heard this. But if you haven't, please listen to YouTube. The first several pages of this is describing what you need to do for 3 questions on the lab, and then the rest of the lab is covering the bulk of the points, and we did do that in class. Anyone else need the lab? Now, also mark hopefully I'll see that and carry it with me when I leave. The reason everything's up here, I'm going to straight from here across the road to my appointment and straight back again. So, David came in. Does anyone else come in that I didn't acknowledge when you got here? Okay. Well, got it. Okay. What I was getting here is I've got some grading I can do while I'm there. I'm going to keep this in my pocket so I'll have it with me. All right. So what today's going to be, as soon as I can finish all this talking, we'll get started and do as much as we can on Chapter 17 in 30 minutes. That's not going to be much. Then I go to my doctor's appointment, okay, and while I'm gone, here's what I recommend. You can finish up any labs you're behind, work together as groups. You can study, get together, and work up your formula and equation sheet, whatever you want to write down for your Chapter 16 test. And you can do that together in a group if you want to, or individually, or whatever. Okay? Then, also your research paper. If you want to run down to the library or somewhere else and work on that, you can. Now, someone estimated, I think it's a pretty good guess, I'll probably be gone, it could be, I don't know, I just don't know how long it'll be. I'm hoping no more than an hour and a half. I'd love it to be only an hour, but I don't know. Yeah. And, well, the thing is, it's just a follow-up visit. I had cataract surgery last summer, and they're just following up, making sure everything is okay, and it is. But I don't know how backed up the doctor is. I don't know if they're going to have to dilate. I imagine they will, and how long that'll take, and all that kind of mess. So anyway, I'll get back as soon as I can. Whenever I get back, for whoever's here, I'll continue with where I leave off at 1:45. Okay? Now, also, at 5:15, for whoever comes back, I'd suggest everybody try to be back by 5:15, because that's when I'll be giving the Chapter 16 test. Okay, so that's definitely will happen. I'll be back before 5. They'll kick you out of there before 5:15, so I know I'll be back by then. And so I hope well before then. So we aren't going to get enough done today to have a lab, so it's just going to be lecture until the test at 5:15. Make sense? Okay. Any questions? Yes. Okay.
Tomorrow, can I come during your office hours?
Okay, office hours tomorrow are 8 to 10. And that's about it. I have you can come during my lunch hour, which is 11:45 until 12:30. That's another bit of time. But after that, I'm in class almost continuously until I have to leave to go to the Birmingham East Campus for a physics class tomorrow evening. And my class ends at 3:45. I have to be out of the building pretty much before 4 o'clock, so I just have time to swap out. So there's not a lot of time there, but so 8 to 10 in the morning or 11:45 to 12:15, 12:30. So I have a full 45 minutes of lunch tomorrow, so it's a nice day. Okay, yeah, so either of those will be fine. All right, any other questions? Good questions, by the way. All right, now, here's where we left off before, if there's no questions. In Chapter 17, Rocks and Minerals, this is beginning of what the book calls earth science. I usually consider kind of geology type portion of the course, okay? We had the preview and all that kind of stuff. You have solid earth material. Now, what we're meaning by that, not counting the water on the surface, we're going to talk about that in the last chapter we covered. Not going to talk about the atmosphere, going to talk about that some in the next to last chapter we covered. So let's just talk about the solid earth materials. And I think we actually mentioned this. It's a non-uniform distribution of matter. It's non-uniform in many ways, okay? You can go south of here and hit what they call the wiregrass region, the coastal plain, and you just have really great farmland, timberland, rich, fairly good soils and stuff like this. You go a little bit in another direction, you hit mountains, okay? You go in another direction, you just go ahead. Now, not just that, if you go vertically, you're going to hit soil for a while, that's solid material, but then you're going to start hitting bedrock. Most of what we're underlain by is limestone. So you'll hit limestone, you may hit some granite. Somewhere in some areas you'll hit iron ore, okay? Some areas you hit coal. Some areas you'll hit a variety of other things. So it's a non-uniform distribution of matter, whether you go horizontally, vertically, or whatever. Now, if you go deep enough, which you never will, you would find a molten core, melted core. This, okay. Why would it's way, way, way down deep be melted? Well, you have all the pressure of everything above, all the layers above pressing down, and remember, nothing is ever static. Things are always moving, always moving. And if you press your hands together, moving them, you'll feel they get hotter and hotter and hotter. Okay? That is what melts the core. It's rock is mostly, and I think we hit this before, our heavy elements, okay? But the main part is iron and nickel. And we're going to see this in just a little bit. We live in a very thin surface crust. You will never get close to the core. The Earth is just way too big. We're in a very thin surface crust made mostly of lighter elements, not the heavier elements. And 8 elements, only 8, make up 98.6% of the Earth's crust. Only 8 elements make up the vast majority. You have little bits of other things, but 8 elements make it up. The rocks and minerals make up most of the solid crust materials. Okay? Now, the title of this chapter is Rocks and Minerals. After this introductory part, we're going to flip them and we're going to do minerals and then rocks. Okay? So it should be minerals and rocks. Okay, so, yes.
This is it about the slide, but I don't. So if I can see anything in the library or find something more interesting that changed my research.
Sure. And what did you choose? Okay, that's all right. Yeah, you can change anytime. Yeah. If you either can't find enough, or you find way too much and you don't know how to narrow it down, or if what you find you say, boy, this is boring, and you want to find something more exciting, absolutely. Or if you run across something, ooh, I wish I'd have chosen that. Choose it. Okay. Yeah, you start with that.
This is my first time hearing about a research paper,
right.
So we can pick any subject that we want to write about in this class.
Right, and I mean, try to aim for astronomy, which could be stars, galaxies, meteors, anything to do with astronomy, or geology, rocks, minerals, just anything to do with geology, or weather, climate, anything to do with that, hurricanes, tornadoes, back on astronomy, Big Bang. I mean, it's just, there's tons of things you can choose from. And then ocean water, the ocean waters, the atmosphere, anything to do with physical science.
Yeah, I know Newton's laws of motion.
Yeah, that's okay. Yeah. Those are good too. They're in physical science. They're in the second part, but yeah, it's still physical science. And we're still using them here. Okay. Let me get Jacob here. Well, he got here, but I'm going to mark him here. Okay. Now, so there is a pretty nice figure 17.1 on page 437. Nothing super remarkable, but turning to 438, this is what we hit here. Okay. Now, some of your books, no, I think it's pretty much going to be the same. Okay. Here is the Earth's crust. Remember, only 8 elements make up 98.6, almost 99% of the Earth's crust. The biggest of these is oxygen. I can almost hear you saying, wait a minute, I thought you were saying we weren't talking about the atmosphere. I'm not talking about the atmosphere. I'm talking about solid Earth material. How is oxygen part of the solid Earth material? Say again?
Yes, it's almost there.
Well, no, but we don't have any solid oxygen, just in one sense, not frozen solid. I mentioned just a little bit ago the word limestone. Any of you familiar with that? Okay. Limestone is calcium carbonate. Okay? Anytime you hear an ATE or even an ITE at the end of a chemical name, that means oxygen. Calcium is Ca, 1 calcium. Carbon is 1 carbon. Carbonate, 3 oxygens. So that one mineral, limestone, calcium carbonate being the mineral, Oh boy, they just keep coming. All right. Kyria came. Justin's not yet. Okay, Eric? Yeah. Okay, it was you. And Donald. Okay. Anyone else come in since I called roll? Okay. So you see, we're talking about oxygen that is combined with other things. Oxygen is a very reactive element. It combines with all sorts of stuff. Water mostly is oxygen, believe it or not. H2O, there's two hydrogens for one oxygen, but oxygen is much more massive than hydrogen. So it's like a mass of water is 16 grams of that. 18 grams would be oxygen. Only 2 grams would be hydrogen. So oxygen is all over the place. Solids, liquids, gases, all over the place. So the predominant mineral in the Earth's crust is oxygen, because it's combined with lots of other things making solid material. We'll talk about some of these later. Number 2, silicon. More than a quarter. Almost half of the Earth's crust is made up of oxygen. Silicon is number 2 with more than a quarter. Now, anything come to mind, solid material come to mind when you think of silicon? Second? Okay. There is a type of lubricant that has silicon in it. I mean, sort of a solid material that's out there. Sand. Sand is almost it's largely silicon. Not majority, it was that. Sand is silicate. Silicon and 4 oxygen. So you see, that's why even sand is more oxygen than is silicon. Okay? But just about all your minerals, soil minerals and other things, rocks and everything, have lots of silicates in them. So there's where the silicon comes in, number 2. Number 3, aluminum. Okay? Again, usually mixed with other things. Has anyone ever heard of the mineral called bauxite? That's an aluminum ore. There's aluminum hydroxide. There is a variety. So aluminum is number 3, only 8.1%, less than a tenth is that. Then iron. Iron is 5%. 1/20th of the Earth's surface is iron. Crust is made up of iron. Now some of that is like in iron ore. The iron minings around here, that was in the crust. But if you look on most plowed fields in Alabama, I know this is true in Georgia, what color do they appear to be? Plowed fields, soil that's overturned, So what color do you think? Brownish, that's for sure. Any other characteristic color? Reddish. What is that red color? It's iron oxide, like rust. That's what gives the red clays their color. Okay? I know he's here. There he is. There's Justin. All right. Now, I hope someone is keeping up with time for me. Okay? Second? You're kidding me. Is that all? Yeah. Okay. Let's at least get through the crust if we can. So iron is number what? 4 now. Okay?
What was number 3?
Number 3 was aluminum. Number 2 was silicon. Number 1 was oxygen. Okay? So any of that red color clays that you see out there, the clays are not made up of iron. The coating on the clays is made up of iron oxide. And so it's not just in iron ore. Calcium, I mentioned, in our crust, especially under where we are, calcium carbonate, limestone. That's the predominant substrate, you might say, underlies the bedrock that underlies most of Alabama is calcium carbonate.
That's why they got so much gypsum around here.
So that's what?
That's why we got so many gypsum plants.
Gypsum plant, absolutely, yeah, absolutely. Gypsum is calcium sulfate, okay? You're absolutely right, okay? Sodium is next. Sodium is just everywhere. You know, sodium chloride, sodium, just about any mineral is, not any, but a lot of them will have sodium in them as well. Potassium just after that, in such small percentages. Magnesium right after those, and then everything else combined, all the rest of your 100 plus elements are in 1.4%. Subtract that from 100%, and that's where you get your 98.6% out of those 8. And if you just look at these two, 75%, okay? Include that, and you're close to 85%. That's incredible, okay? 98, almost 99% of the Earth's crust is made out of 8 elements. Okay. Now, do we have time to go to the next one? 2 minutes. Let's see if we can get it done. The whole Earth, okay, that includes the crust, but mostly includes everything beneath the crust, and we'll talk about what that is later. A third of that is iron. It was just a little bit here, but the vast majority of what's inside the Earth, the core, iron and nickel, there it was. The outside the core, iron is predominant. Oxygen falls from here to there. Mostly you have oxygen in the minerals further down, but not nearly as much. Silicon comes in number 3 now, and it's dropped to there. It's a light mineral, so it's going to be more on the surface. Look who else came up besides iron, magnesium. And we'll talk about the minerals inside the Earth as being ferromagnesium minerals. Ferro from iron, Fe, magnesium here. Okay? And then, as we mentioned earlier, nickel, especially in the core, nickel is a very high prevalent. Calcium, not as common inside, but it's still a fair amount. Aluminum next, see it dropped. It's a light mineral, light element, so it's not as much in the core and the interior. Sodium really dropped, and then everything else. And you see that would include your potassium, magnesium, not magnesium, potassium, and all those other minerals, elements would be in that part. So, say again? It's time. Okay, for those who came in late, I explained this earlier, I've got an eye appointment just across the road here. So I'm going across the road, have my eye appointment, I'll come back. Whoever's still here or comes back, I will go on and continue the class from this point, and then at 5:15, I'll give the Chapter 16 test if anyone is still here. If no one's still here, I'll just keep talking on Chapter 17, but hopefully someone will be here to do the test. All right, so what I'm going to do is pause this. I'm not going to upload it.
I said they're good.
Okay. All right. Now, let me wait till it comes up. Any questions on anything we've done so far?
You're not going to try to read on it.
I'm sorry?
You're not going to try to finish that out.
Yes, it is. It's about this week.
Are you going to try to read that?
Yes. I mean, I can read that. I just can't see into the bright light.
Please don't.
No.
Okay. Okay. I don't think I want you here. Brandis. Okay. Okay, got it. How are we doing? Now, I know a few of you weren't here for the first half hour, okay, before I had to go to the eye appointment. And if anyone needs to see an excuse, I have my thing here. All right.
Go back to it. Do you have any previous slides before this?
This is the one we started on today.
Oh,
Yeah,
let me get the cord.
Oh, that one. Okay. That one we had last time.
Professor Fowler,
Yes.
you know, when we're doing this, I mean, this is, some of these chapters are extremely long, and you say we can only have one sheet with both, everything. That's not enough to put everything over.
Okay. If you need 2 sheets, you can do it, but when you get too many sheets, you spend all your time looking at all that data on other sheets, and I don't know. It just.
But you can't put, I mean, the chapters are long.
Right.
And you don't know what's going to be on the test.
Right.
So take good notes.
Right. If you need 2 sheets, you can use 2 sheets, front and back. But I just warn you that sometimes too much, and you can't find what you're looking for. But all right, did you finish with this?
Oh, I already had the picture.
I thought you did. Okay. All right. Now, I think we finished this slide last time. We were talking about the interior. The thin surface crust, 8 elements make up 98% of it, and in the whole Earth, though 1, 2, 3, 4, 5, 6, 7, 8 make up 98.1%. So it's still largely focusing on certain elements. Okay? Now, this is, I believe, Brianna, right?
Yes.
Okay. I've just had my eyes dilated, so I'm not, especially looking into the sun, cannot see very well. Okay, and that's why I've got the shades on. Okay. Now, any questions about this slide before we move on? Okay. I don't know if that was me or what. Okay. Get this out of my pocket. Okay. All right. As I said before, and before some of you came, the title of the chapter is Rocks and Minerals. But the order of the material presented is minerals and then rocks. So we're moving into 17.2 now, which is minerals. Now, if y'all don't mind, I know I'll be further from the microphone, but I don't have to look into the sun. Minerals, here is the earth science definition for what a mineral is. Number 1, naturally occurring. Naturally occurring. Okay, that means it's not something man has made. Okay, there is a lab over at UAB, or there was a few years ago, that they made synthetic diamonds. Those diamonds, though they look like other diamonds, they technically would not be classified minerals because they're man-made. So these are naturally occurring, inorganic, solid element or compound with a crystal structure. So let's take it word by word. Inorganic, what does that mean? Not coming directly from life. So for instance, even though your teeth or your bones may seem very hard and almost like a mineral, they're organic because they're in human bodies, okay? Even if they come out of a human body, okay? So it must be naturally occurring but not coming from living organisms, or at least not directly. I say that because I've mentioned limestone a time or two. Limestone originally was the fragments of bones and shells and things like this, which are coming out of living things, okay? But the mineral that makes up limestone, calcium carbonate, that's been so long since it was part of something organic that it is counted a mineral. Okay? So there's inorganic, solid. Okay? As I said, the water on the Earth's surface is not a mineral. Okay? That's not what we're talking about. We'll talk about that in the last chapter we did. Okay? The atmosphere, that's gases, not counting those. Okay? We're talking about solid elements or compounds. To be a mineral, it either is a pure element, not that many of those, but lots and lots of different compounds. Okay? And here's the big one, with a crystalline structure. Now, what does that mean? Okay? We'll get back at it in just a minute. Let me first go back here. Naturally occurring cannot be synthetic. So this bullet is balancing that. Not directly produced by a living organism, that's what it means, inorganic. And must have a regular repeating pattern, that's what it means, a crystalline structure.
Inorganic means it's not natural.
No. Inorganic means it's not from living organisms. Okay. Not from living organisms. Not directly produced by a living organism. Sometime way back in the past it could have been, but not directly. Okay?
Yes.
So this crystal structure means you have some sort of repeating pattern in the way those solid elements and compounds are put together. Okay? And one example is halite. That is something, I'm trying to see if anyone has any foodstuffs in here. I don't see any. I see drinking stuff, but no foodstuff. Okay? Anyone know what a common name for halite is? Table salt. Okay? Sodium chloride is salt. Okay? Halite is the mineral that we get salt from. Okay? Now, this next slide illustrates what we mean by a repeating pattern. Now, there's one fairly serious error on this slide, okay, and I'll see if any of you can find it. Okay, David Wright, I can't see well because my eyes have been dilated. Okay, this is an example of halite. The yellows are the sodium ions, which is pretty appropriate because sodium is a yellow metal, very soft metal, and chloride is a chlorine. Green would have been better because it's a green gas, okay? Now, regular pattern. Now, this pattern we'll talk about a little bit later is a cubic pattern because they're all arranged in little bitty cubes. And notice that every sodium ion is directly linked to only chlorine ions, okay? Every sodium is directly linked to only chlorine. And every chlorine is only directly linked to a sodium. Okay, I used the wrong, okay? Only directly. Has anyone seen the error yet?
They're not directly.
Okay? This one right here. That should be yellow because it's connected to blue, blue, blue. Okay? Sound like Elvis Presley, don't know. This should be a yellow. That should be a sodium ion. Graphics person just got it wrong. Okay. Now, that structure is repeated over and over and over. That's what we mean repeating pattern. And that would be a form of a crystal. Now, if you ever choose to do so, if you have a really good magnifying glass, sprinkle a little of that salt in your hand, look at it, and you see every one of those crystals is made up of little bitty cubes. Okay? Every time. Okay. Now, let me say a little bit also about this. Sometimes that repeating pattern is very, very small. Other times it's pretty large, okay? But it must be repeating. There are some things that you would normally think is a mineral that really are not. For instance, what about that window glass? Or as my grandmother used to call it, window light. Okay, that's what let the light through. Would you say that's a mineral?
Yeah.
Say again? It is made out of sand. So would it be a mineral?
Yeah.
Okay, the sand was a mineral. What they've done with the sand, they heat it to very, very, very high temperature so it melts, and then they cool it very quickly. When they cool it very quickly, it does not have time to go back into the crystal structure that sand has. So no, the glass is not. And besides, it's man-made. Okay. So, but it wouldn't qualify anyway unless you let it cool very slowly. Then it would form back into the crystal pattern. Okay. The repeating crystal pattern has those blocks very well organized. Okay, whatever the blocks may be. Okay. Now, they're going to talk some about the crystal structures. And crystal structures can be made of more than one kind of elements. For instance, I mentioned calcium carbonate. The 8 means oxygen, so that would be calcium, carbon, and oxygen. Or it can be only one. For instance, diamond is carbon only. Diamond is carbon? Well, we talked about this in the when we talked about white dwarfs, remember? Diamond is the same as that soot that's in your chimney. Okay? See, can you believe it? The element is pure carbon. However, it's the crystal structure that makes the difference. Has anyone ever heard of graphite? What is graphite used for? Okay, writing is one thing. The lead in your pencil is not lead. It is graphite mixed with kaolinite, which is a clay mineral. Okay? The dark color is the graphite. The hardness comes from the clay mineral, the kaolinite. Okay? Now, that same graphite, I don't know if any of you have ever used or heard of it, it is also a lubricant. Graphite can be used because it's really slick stuff. If you've ever felt of the soot in your chimney, it's slick, really slick. It can be used as a lubricant. Okay? It's a two-dimensional structure. The carbon is arranged in a planar type structure, regular composition, but the planes slide over each other very, very easily. However, diamond is a three-dimensional structure. Very different looking. I mean, diamonds are clear, not sooty looking, okay, not black like pencil lead. And they are very abrasive. There is no naturally known material that's harder than a diamond. So they are intensely abrasive, whereas graphite is a lubricant, which keeps things from abrading. So very, very different because of their structure. Now, quartz is a mineral made up of silicon and oxygen. Silicon in the middle and then up to 4 oxygens around it. Now, it's not always a 1-to-4 ratio because one silica could share this pair of oxygens and the other silica could share it and another, so several silica can share some of those oxygens, but that's what quartz is. That's what sand is made from, and that's what the window is made from also, is silicon dioxide, basically. Okay? Now, the classification for these crystal structures is based on their surface symmetry. Now, don't get bent out of shape on these. These are difficult words. I'll try to explain what they mean basically. I'll show you pictures of them, but don't get bent out of shape. This isn't worth trying to memorize any of these right here, because that is pretty heady stuff. And here's the picture. Okay? 6 major systems. There are other variations on this, but 6 major. Isometric. Okay? Isometric. Now, does anyone know what the prefix iso means? In pressure, we talk about atmospheric pressure, isobars.
That's the.
Say again? You know that one, right?
Okay.
Yeah, and in climbing mountains and stuff, you talk about isoclines. A triangle that has 2 sides the same is called an isosceles triangle. Iso means the same. Okay? So metric is to measure. So what isometric structure is one that all the sides are equal. They're the same. And here's a cube. And that's what makes a cube a cube. All 6 sides, left, right, front, back, top, bottom, all 6 sides are the same. All lengths of the, and as it says here, these are surface symmetries, based on surface symmetry. All the edges are the same. And not only all the edges are the same, All the angles are the same. These are all right angles here. Okay? That's what makes a cube. And what cubic structure did we just see? Salt. Okay? Halite was a cubic structure. Okay? And that's a pretty major one. Okay? Here's another isometric. This is, I can't read that. Octahedron is what it's called. Octo means 8. Hedron basically means sides. This is made up of 8. Yeah. I don't know why it does that. It's coming back. Okay. It's hard for me to see. Okay. 1, 2, 8 equilateral triangles. I believe they're all equilateral. You got 4 on top and 4 on the bottom. That's where the octahedron comes from. 8 sides. All these lines are equal length. That would make equilateral triangles. And all the angles are equal length. That's a octahedron. Another type of isometric symmetry. Here is a tetrahedron. I think I can't see it, but that looks like a tetrahedron. These are 1, 2, 3, 4. Tetra means 4. 4 equilateral triangles. All the lengths are the same. Now they don't look like it because it's 3-dimensional on a 2-dimensional plane, but this goes back into the board. So that's a tetrahedral structure. A lot of your silicates are tetrahedral structures. Called silicon's in the middle, and then you have 4 oxygens, 1, 2, 3, 4 on the vertices, and that's what makes, and the silicon's in the middle. And then some of these sides are shared with another next silicon. Okay, and this is a. Let's see if I can find it, because I sure can't read that on the board. Let me see if I can read it here. Dodecahedron. Okay, that is a 12-sided figure. Okay. And this is hard to see 12 sides, and it's really hard to get a good perspective on this. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12-sided figure. All the lengths are the same. Now, it sure doesn't look like all the angles are the same, but all the lengths are. To me, that looks a lot like a soccer ball. Okay, it's not the same, but it's somewhat similar to that. Now, all you were in here before. I'm trying to make sure I get everybody when they come in. Okay. I can't remember which slides. See, your book doesn't have these anymore. The older edition did, so don't sweat these. They quit even showing them in the book. But just wanted to, so if you ever run into them, you'll know, oh yeah, I've heard of that before. Now, the next is hexagonal structures. Hex means 6. So these are 6-sided figures. Here's a hexagonal prism. There's 1, 2, 3, 4, 5, 6. Okay, not counting top and bottom. There's 6 sides. And this, to me, looks awful much like a cube, but it's not. It's a rhombohedron. Now, anyone know what a rhombus is? It's a square that you sat on, and it went over like this. So it's got equal length sides, but the angles aren't equal. Okay? So that's why this is a rhombohedron. It's got 6 sides. 1, 2, 3, 4, 5, 6. Well, so did that, but there everything's equal. Here the angles are not equal. Okay, so a rhombohedron is a hexagonal structure. Okay, next is tetragonal. This is 4-sided. And here's a picture of a 4-sided. 1, 2, 3, 4. Now that's on the lateral side. We also have 4, 2, 3, 4 at the top, 1, 2, 3, 4 at the bottom. They may or may not have the top or bottom, but that's a tetragonal structure. This is a tetrahedron. That's a isometric structure. This is four-sided, tetrahedron. Tetragonal, I'm sorry, tetragonal.
I found it.
Yes.
We weren't gonna be,
No, yeah, don't sweat these. This is just to, if you see the words again, say, oh, I recognize that. But don't think you have to know these. Okay? The next one listed here is orthorhombic, and so far I haven't figured out what that is, except the rhombus again are not equal angles. Okay? Ortho, I can't remember what that prefix is supposed to stand for, but I think several things are not equal in it, but it's still a crystal structure that does repeat itself. Then the monoclinic and triclinic, again, I can't for the life of me figure out why that's called a monoclinic. Mono usually means one, and I can't see one of anything in that. This is a prism that doesn't fit the others. And this is a triclinic, and frankly to me that looks a lot like some of these others, except there's something, and I don't know what tri usually means three, I don't know what the clinic means, but those are just another type of a crystal structure. A regular pattern that repeats itself. So don't sweat knowing these and being able to pick them out, but just be familiar if you ever hear them. And you'll hear them. I mean, in this chapter, it'll talk about, just like it talked about salt crystals, halite being a cubic structure. When you hear cubic structure, you know that's isometric. But you don't need to, I mean, there's nothing that's you're going to be required to reproduce that. Okay. Anyone need this any longer? All right. Now, here are some pictures. I don't think all these are in your book. The one on the right is figure 17.5, which it was in this text. 17.4 is the top of the salt shaker, which are halite crystals. These are also halite crystals. It's just an older figure. Blown up by magnification, I believe, and then they've used color so you can see it a little bit better. But you see, every one of those, I can't see them well because of the glare, but these are little cubes. So the halite is a cubic structure. And then let's take a look at these. Okay. I'm going to go back here. Tetragonal structure, this one, four-sided. Okay. Let's take a look at these quartz crystals. Okay. Now, I can't see well enough, but I've seen them before. You can see 1, 2, 3, 4 sides here. There's that little pointed part. 1, 2, 3, 4 sides here. There's the part, and then here's the pointed part down here. 1, 2, 3, 4. Okay? I wish I could see this better to point out, but when we do the lab for this chapter, I'll have some samples that you'll see actually the rocks that contain some of these quartz crystals, and they're really incredibly pretty. Okay? There you see 1, 2, 3, 4. That's that point again. Okay, and you can see the quartz going down into here, but it's being surrounded by other things. Perhaps other quartz crystals or other crystals. I'm sure these are too. I just can't make them out because of my vision. I just can't see it today. And even looking at it in the book, I can't. Yeah, that's worse. You just see smaller versions of the same thing. Okay. So those are just examples of different crystal forms, crystal structures. Now, going back to the concept of minerals, okay? In the surface of the earth, okay, we have two major classifications of types how these minerals are put together. The first of these are silicates. Remember that silicon and oxygen. The ATE stands for oxygen. Now if you remember back on the surface of the earth, 46% of the surface was oxygen, 27% was silica. Hey, that makes up most of your silicates right there, containing mostly silicon and oxygen. Now, there can be other impurities and other things in it, but these silicates make up 92% of the Earth's crust. So obviously, a little bit more is in there besides silicon and oxygen. That would add to only around 75%, but some other things like potassium silicates and sodium silicates and others. So there are other elements in them, but the silicates make up 92% of the Earth's crust. So the other 8% of the Earth's crust are non-silicates. We'll get there in a minute. So these are based on the silicon-oxygen tetrahedral unit. Remember I said silicon's in the middle, 4 oxygens equally gather around it, making those little tetrahedrons, which is one of our shapes. Now there's 4 major arrangements of these. The isolated tetrahedrons, which may be those sand particles that get in your shoes at the beach and really hurt, okay, because they're really pointed. Isolated tetrahedrons. You also have chain chain silicates. Now, some that hopefully you're not too familiar with, but you've heard about, are asbestos. Asbestos is a chain silicate, and those fragments of certain types of asbestos, when embedded in your lungs, can really give you issues. Asbestosis, silicosis, there's lots of things that you don't want to happen with those. The sad news is there's a lot of asbestos that is absolutely non-harmful at all. But because it has the name asbestos, no one will touch it with a 10-foot pole. So they become bad. But I can remember, I don't remember specifically, but generally I can remember back when I was young, asbestos was considered a wonder material because it wouldn't burn. So you could enclose things in it and you couldn't set it on fire, okay? So it was considered to be a fantastic material until people started getting lung cancers and other serious illnesses from it, and then it became forbidden, okay? Now, sometime or another, this was years ago, I think I was at my wife's sister's house. We were over there, and they had rented some old TV shows that y'all probably wouldn't even remember. George and Gracie, Burns and Allen, some really old shows. And when the shows were showing, they were fun. But then they showed the commercials. And there was one about asbestos, the wonder material, It was just playing it up like crazy. I thought, whoa, no one will touch that now. So those are one type of chain silicates. Halloysite is another. There are several other chain silicates. Then you have the sheet silicates. Now, we talked a little bit about when I mentioned kaolinite in your pencil lead that gives the hardness to it. The sheet silicates are mostly your clay minerals. Your clay minerals are made mostly of silica sheets and alumina sheets, okay? And they build on each other, and that's why clays get really slick when they're wet, because they slide past each other very easily, and also can become very impermeable to water if you run over them when they're wet. That's what makes mud puddles and things like that. So sheet silicates, one example of those are your clay minerals. And then you have the framework silicates, which would be more like I could name some minerals, but you probably wouldn't recognize them. But for instance, the silicates that make up granites, that's a framework, three-dimensional structure there. So isolated tetrahedrons, chain silicates, which are one-dimensional mostly, sheet silicates, which are two-dimensional, and framework silicates, which are three-dimensional structures. Okay? Now, the tetrahedron I was talking about, here it is. Silicon in the center and oxygens around here. Now, don't think that is how it really looks, okay? Silicon tends to be a +4 charge, an ion with +4, meaning it's lost 4 electrons. Well, if its nucleus has a very strong positive charge, and then you've lost some electrons, that nucleus pulls those electrons closer and closer together, so that silicon in the middle is really small. Whereas the oxygens on the edges, on the vertices, they are plus or minus 2. They have 2 extra electrons. So they get really swollen because those extra electrons try to get as far away from each other as they can, so they're actually quite big. So if you really saw this, this would be sort of like the Michelin tire man, you know how he's made up of tires? This would be 4 big old balls here with a tiny little ball in the middle. And one of the next slides will show actually does a lot better job than that. That's where you get the tetragonal structure, the tetrahedral structure. All right. Here are the ones that show isolated tetrahedrons like this. Now this is the one I was talking about. See these big old bulbous oxygens and that one little bitty green silicon in the middle. That's far closer to what it was in the previous one. And this doesn't look like a tetrahedron because you think of tetrahedrons as being flat-sided. These are not flat-sided, they're just four-sided. That's what tetrahedron means. So those are your isolated tetrahedra. Here are your chain tetrahedra, chain silicates. And notice here, there's one pair of these oxygens here get shared by this and that. And then one pair gets shared by this one and that. One gets paired. And that's why it's not a straight chain, it's a what they call a serpentine-like chain. And there is a mineral called serpentine, by the way, that is one of these chain silicates. Then your sheet silicates would be more like this, or if you had them stacked on top of each other, that would then be a framework silicate. Okay. So these illustrate those pretty much, except both of those could be sheet silicates. You'd have to have 3 dimensions to see the chain silicates. I mean the framework silicates. All right. Silicates. 92% of the Earth's crust made up of silicates. That leaves how many? 8% for non-silicates. Okay? Now again, these are all minerals. They have the chain structures, the crystalline structures and stuff. But the non-silicates have no silicon-oxygen tetrahedrons in their crystal structure. Okay? They have other things in there. They're all going to have oxygen pretty much, okay? Just about all, but not silicon-oxygen in the crystalline structure. They make up 8% of the Earth's crust. So why do we put so much attention on them? Because some of them are pretty important. Now, there are 8 groups of these non-silicates. Now, don't think they're 1% each. They're nowhere close. These are from most abundant to least abundant. The first of these is your carbonates. Now, I've already mentioned that. Your limestones, okay? Now, limestone is actually a rock, not a mineral, but it's made up of carbonate minerals, mostly, okay? And this would mean carbon and oxygens, okay? Now, there's many kinds of carbonates. There's calcium carbonate, that's limestone. There's calcium and magnesium carbonate, that's dolomitic limestone. Someone mentioned gypsum, right? That's calcium, different one, that's sulfates. You could have sodium carbonates, you could have potassium carbonates, you could have lots of different carbonates. The primary ones are calcium and magnesium. Most abundant. Like I said, the bedrock that underlies most of Alabama is limestone, which is made predominantly of calcium carbonate with some. Now there is actually a town north and a little bit west of here called Dolomite. You would think that it would have to have dolomitic limestone, which is calcium carbonate with magnesium carbonate.
You have that? Oh, that's just the name.
I assume that there. I mean, there's limestone mines all over the place,
Right.
and I bet you the ones up there must be dolomitic, but I don't know that for sure. Why else would they pick a name like Dolomite?
Yeah, it's still pretty big in that area too.
Yeah.
So it's cool.
Yeah, it's a pretty big guess. But you see, It's what makes this area of, yes.
Is jasper a stone or a flower?
What's that again?
Jasper. Is it a type of mineral?
What are you saying?
Is jasper a mineral or is it a
Oh. There is a mineral named jasper. Now, are you asking, is that where the town got its name?
Oh, yeah.
Yeah.
We're talking about dolomite.
Yeah, I know.
And meridian.
Okay. I can't answer that. I can't answer the question because Jasper is a common person's name too. I've never heard of anyone named Dolomite, but I have heard of people whose either first or last names are Jasper. So Jasper could be named after people or it could be named after a mineral. I don't know which. Okay. Now I just had my eye exam, so that's why I've got the shades on. So I can't really make out. Is it Maya? Kaya, I knew it was Kaya. Okay, I thought that's who you were, but I've just got to find you now. There you are. All right. So far, we're only missing Bridget, right? Can't read. Zach and Antonio. Now, I thought somebody said Antonio was coming back. Is that right?
Yeah.
Okay, so hopefully he'll be back. So good attendance today in spite of the fact I wasn't here much of it. Now a lot of people did leave because they didn't know how long I'd be at the doctor's and had to go. So that covers carbonates. Another type of non-silicate, you see carbonates don't have silicon in them in large amounts. Okay, no silicon, oxygen, tetrahedrons in that crystal structure. Sulfates, this is your gypsum. Calcium sulfate is gypsum. Anyone know what magnesium sulfate is? I bet you your grandmother might know.
I've heard of that.
Say again?
I've heard of it.
Epsom salts. Epsom salts are magnesium sulfate. The reason I say grandmother, my grandmother used to use it. She would have bits of gout, and she would soak her feet in Epsom salts. But then she found out that Epsom salt, the water left over, was really great for putting on her African violets. And she had the most beautiful African violets I've ever seen in my life. Until one day she had too strong a concentration and she killed them. But then she started growing them back again. Okay. So anyway, sulfates, gypsum, concrete block. If you were to analyze what's in here, the minerals that are in there, you would find, because sand is in that, you would find silicates, but you would also find a fair amount of calcium carbonate, limestone, that's your carbonate, and I bet you would find quite a bit of gypsum in there as well, in that calcium sulfate. So that would be your sulfate. These are your non-silicates, not that predominant, but okay. Oxides. I said at the very beginning, and if you think about it, silicates are mostly oxygen, carbonates, mostly oxygen, sulfates, mostly oxygen, and of course oxides are largely oxygen. Okay? Some of your oxides are common ones, iron oxides. There's actually two types of iron oxide. One of those is the red, the rust looking, that's high oxygen, that's Fe2O3. 3 oxygens for every 2 irons. And that's the crystal structure. But you also have ferrous oxide, which is FeO, 1 to 1. Okay? Now, do any of you have any, and it won't be the mineral because it's organic, but have any iron oxides associated with you? Every one of them. How?
Is it in your blood?
In your what?
Bloodstream?
Blood, absolutely. What is one of the key components of your blood? Iron. And where does it exist? In hemoglobin. Your hemoglobin. Just like anytime you go to the doctor and they do blood work, they're going to check your hemoglobin. If you just go to a regular thing, they're going to take a drop and see whether it floats or sinks in a certain liquid, showing whether you're anemic or not. Do you have enough hemoglobin? Now, what does hemoglobin do for you in your blood? Second? I can't hear you. Okay, how does it do it? What does it do
Iron,
for you?
put iron in it, though.
Say again?
Iron.
Okay, the iron. What does it do for you? That in the hemoglobin?
Keeps your blood thick, doesn't it?
It's what?
It makes your blood thick.
It probably does somewhat because it's pretty hard. Now, let me describe it
Keeps
for
you
you.
warm.
Not quite. That's metabolizing. Okay, that's your sugars and your starches. Okay, if you picture a claw, a claw, and in the middle of the claw is an iron. Okay, now around this in the claw are various other things, including oxygens. Okay, oxide. Okay, now what two types of blood do you have?
Red and white.
Blue, right?
No.
White.
Red. Oh, those are blood cells. Okay. I said types of blood. You have venal blood and arterial blood. Now, what's generally the difference between those?
One is carrying oxygen, the other one is carrying carbon dioxide.
Okay, very good. What's the difference in colors? Say again? One is blue and one is red. Which is which?
The blue is the side that when your blood comes out, it turns red.
Yeah.
Because it hits oxygen.
Okay, because it hits the oxygen. Perfect. Okay? What the arterial blood is taking the oxygen from your lungs, and what is happening? That hemoglobin is picking up an extra oxygen, turning red. Ferric oxide. Okay? Taking it to your muscles, your eyes, your ears, whatever is using it, okay? And then giving up that oxygen so you can metabolize, which keeps you warm and gets you moving and that kind of stuff. And then it turns blue, and the venal blood comes back.
And that's where the carbon comes from this particular vein in your lungs, the carbon in the dioxide in your lungs. Am I saying that right?
Okay. Yeah. There is
I
some.
got confused there.
There is some arterial blood that is pumped blue from your heart to your lungs.
Right.
Okay. But most of the arterial blood is pumped from another chamber, the ventricle in your, and pumped throughout your body. And that's the red arterial blood. The venal blood is mostly.
But CO2,
Okay.
I think you get it from here. I think it's in the lungs.
Okay. Yeah, the CO2 is removed. I don't know all the physiology of that. I know the hemoglobin takes the oxygen and then gives it up and comes back blue blood. Okay, comes back as venal blood, ferrous oxide, and so that's just one type of oxide. And I grew up in Georgia, and on our farm in Georgia where my parents built the house, there was a field next door, next to that, and that hillside was as bright red as you could ever imagine. But then at the base of that hillside, it was grayish. The soil was really grayish looking. I thought, all the sand washed off the hillside into the valley down there and was grayish color. No, that wasn't it. The iron on the hillside, ferric oxide, very oxygenated, in other words, bright red, and when it got down here in a swampy area, the oxygen left and it became ferrous oxide, just like red blood, blue blood, okay? And it's pretty amazing. Now, there's lots of other oxides besides iron. There is aluminum oxide, there is potassium oxide, there's just about any metal you could name will also have an oxide with it, okay? So that's that. Then there's the sulfides. Now, what's the difference in sulfates and sulfides? Okay? Fate or fight mean oxygen. The oxides, of course, have oxygen, but it's something else combined with oxygen. Sulfides is something else combined with sulfur. Okay, like one of the most common of those is what?
Sulfur dioxide.
Now that would be an oxide. Okay, sulfur dioxide, that would be an oxide. The sulfides would be, for instance, has anyone ever heard of hydrogen sulfide? Now this is not a mineral because this is a gas. Hydrogen sulfide. I bet you have smelled hydrogen sulfide. You know that rotten egg smell? That's hydrogen sulfide. In fact, most of the strong odor in lots of things will be hydrogen sulfide. Okay? Stay away from that. But other sulfides in minerals, has anyone ever heard of fool's gold? That's it's a pyrite, okay? Iron pyrite, okay? It looks just like gold, but it's not, okay? Fool's gold. That's a sulfide, okay? Halides, okay, I don't know how many of you have your books, and I think somewhere near the back of the book, they put the periodic table. I know I asked them to, but they kind of hid it, and I can't remember where they put it. You got it? Yes. Okay, it's somewhere near the back. Mine's on the inside the back cover, but I don't know where they put it there. Let me just mention a few of these things to you. Here was your silicon, right here, Si, and that was your silicates. Here's your oxygen over here. That's the eights and the ites and the oxides all have oxygen in there. Here's your carbon, carbonates, silicates. We're going to get to another one later. But just about any of your metals here, sodium carbonate, sodium sulfate, I mean, these will combine with those. These will combine with those. Okay? Now, sulfur is right here underneath oxygen. So your oxides, anything that combines with oxygen, magnesium oxide, sodium oxide, potassium oxide, name it. It'll combine with oxygen. Or it may combine with sulfur. Then it would be a sulfide. So the IDE means the oxygen and the sulfur at the end of the element. Okay, compound. What are your halides? Well, that's a huge class. Remember, we have halite, which is sodium chloride. Well, this next to the last column in the periodic table, column 7, fluorides, chlorides, bromides, and iodides. Now, you could have actinides, but they're very rare. So those first four, fluorides, chlorides, bromides, and iodides, those are your halides. It'll be sodium chloride, sodium fluoride, sodium or potassium bromide, whatever you have, you combine one of these with one of those, and those give you your ides. That means that's the last thing in it. Oxide, same thing. Sodium, oxide, whatever. Now, go back to your eights, okay? These have lots of oxygens in them. Phosphate. So here's phosphorus right here, just next between silicon and sulfur. Phosphorus, 1P, 1 phosphorus, and 3 or 4 oxygens. Lots of oxygens, the phosphates. Now, does anyone know a common use for phosphorus? Or any of you gardeners?
Fertilizer.
Huh?
Fertilizer.
Fertilizer, exactly. Phosphate fertilizers. Okay? When you go to buy a bag of fertilizer, you'll typically see 3 numbers. 5, 10, 15, 10, 10, 10, 15, 5, 2, or whatever. Okay? Those 3 numbers. The first number is nitrogen, which everything needs to make protein. Okay? The second number, and I always get them crossed up, I think is potassium, and the third one is phosphate. Okay? It's one of the essential elements for plant growth. Absolutely essential. Okay? The mineral that most of our phosphates come from is called apatite. Yes?
So, since we're on nutrients and fertilizer for plants, I have a lucky bamboo tree at home.
A what tree?
A lucky bamboo tree.
Okay.
I had it for 8 years.
Uh-huh.
And the first one I bought, the lady who was an expert, said to pour some green stuff in. And when I did, it killed my bamboo tree. So what I've done over the past year with my second bamboo, I just watered it and it just grew.
Right.
So is there any minerals and stuff in the water and the rocks that the plant is consuming?
Okay, that's an excellent question. If you think about what most plants are, they're largely carbohydrates. Carbon, hydrogen, and oxygen. The carbon they get from the carbon dioxide in the air, and the hydrogen and oxygen they get from the water that they pull up from the soil. So most plants are mostly carbohydrates, not much fertilizer to them. But they all need fertilizer for something, okay? For instance, those little green leaves that make plant and your bamboo or whatever, they have a little structure there that's essential for every green plant. Anyone know what I'm talking about?
Say every or
Every green plant. Every green plant.
It's chlorophyll.
Chlorophyll, that's exactly what it is. Now chlorophyll, yes. I'm sorry. 3:45? Okay, so it's time to call roll. Oh man, I'm doing way too much talking, am I not? Okay, let's see who we still got here. Bridget didn't make it in today yet. Maybe she'll still come. Brianna is still here. Jerome is still here. Hard to read. Asia is, yeah, there she is. You moved, okay. All right, still here. Jacob, I think we lost, didn't we? Okay. Oh, he's going to come back?
He said he was going to make like a banana and split.
Oh, man, okay. Make like a tree and leave, okay. Okay. All right, Kaya is still kind of here, okay. Okay. Rakiria, it looks like we may have lost her. Justin is mostly here. All right. Hard for me to see. Sherlanda, I thought was coming back, but maybe she'll be here later. Tarsha's still here. Eric, looks like we may have lost him, at least for now. Zach never made it in. Katie is still here. Brandis is still here. I hope I'm still on the right line here. Miss Lewis is still here. Antonio hasn't made it in yet. Now you said he was here, but I haven't seen him yet. David is still here. Isn't that David there? Okay. Can't get his attention, so he's mostly here. All right. Tiffany is still here. Okay. Kaylee indicated she probably wasn't coming back. She lived, what, an hour and a half away, so she wasn't going to hang around that long. Donald looks like we may have lost, and Shikaya is still here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4, 6, 8, 10, 11. I thought we had 12. 4, oh wait, 7, 8, 10, 12. Got it. Okay. And there may be more coming in closer to test time. All right, so there's the phosphate. Oh, I was mentioning phosphate. The main mineral that phosphate comes from is called apatite. Now, it's not the hunger appetite. That's with an A. This is with an E. No, vice versa, okay? But anyway, phosphate, that's one of those. Okay, let me back up. One of the biggest areas of phosphate mining that I know of in the U.S. is on what they call the Bone Ridge or Bone Valley or something like that in central Florida, going right down the middle of Florida. Okay? That was all mostly deposited from ancient marine life. And remember I said to be inorganic, it couldn't have come directly from organisms, but this came far enough away that it has become inorganic now. So anyway, from ancient bones and stuff like this, you get these phosphates. The sad news is that most of the easy to reach phosphate mining has been mined. And where are we going to get the fertilizer phosphates we need to feed a planet that keeps growing by leaps and bounds? I don't want to sound like the agent of doom, but I wouldn't be at all surprised if one of the next big tragedies will be lack of phosphate fertilizer.
It won't
Could
because
help.
they discovered
What's that?
some in South Africa.
What's that?
They discovered a phosphate mine in South Africa not too long ago.
Really? Okay, that may keep us going a bit longer. Yeah.
Which is going to improve what I was going to enforce more emphasis on what I was going to say. Just because there's one area that doesn't have that we use all of them doesn't mean that there's another area that we don't know of.
Right, exactly.
Like if we use all the gold mines up in Sierra Nevada, somewhere else got a lot of gold.
Okay.
Or the minerals, quartz, crystals, diamonds.
Right.
There's always somewhere else
Okay.
that has those minerals, especially with oil.
And I'm glad you mentioned Africa, because one of the richest mineral nations in the world is one of the poorest nations in the world, because they've been ripped off repeatedly by first colonizers and then others. And that's the Congo. The Congo has more rare minerals than just about any other place on the planet.
Why is that?
It's just where they were. But Belgium, I mean, I hate to use a term like this, they raped them. They just,
You're exactly right. That's
Yeah.
the perfect term to use.
yeah. And boy, it was criminal what they did. Okay. But then ever since then, they've never had a stable government for long enough. They did have, wasn't it Mobutu, for a while, but he was just ripping off his own people. Just as bad, he just modeled himself after King Leopold of
Because he was trained by a crook.
Yeah.
he was what?
He was trained by a crook.
Exactly. And he perfected the crookedness. Okay, but it just happened over and over. But and right now the Chinese are going in there, and they are pretty much
Doing the same thing.
They build nice roads and everything else for their benefit. Okay, and they are just ripping off
And all the minerals out there.
all kinds of rare earth minerals, all
And
kinds
leave
of
them
stuff.
barren, don't even have, I don't, the thing that affects me the most is that they have the audacity
Right.
to leave nothing.
Nothing.
I mean, absolutely nothing. To me, the thing that would make it better if they came in and gave them something.
Right.
Left something.
Mm-hmm.
But how can you just come in and, like you say, rape them?
Yeah.
And leave them just barren nothing.
It's
Yeah.
like going to China and taking all their minerals and bamboo trees and not leaving them nothing.
Yeah, but
That
that ain't happening.
Okay.
That ain't happening.
Yeah.
You're talking about reality.
Oh, yeah.
That ain't happening.
I took roll, but I didn't give y'all a chance to have a break. Do you need a break? I mean, we've been going at it quite a while. Let's take a quick break. Let me say this about that though, while we're doing it.
Thank you so much.
What we're just talking about, the Chinese, at least the Belgian and whoever you call them, they came in and they basically raped the people. They used them and paid them almost nothing. What the Chinese do, they come in and bring Chinese workers, and that's who they pay to do the thing, and then they leave and take the workers with them. So yeah, you're right. They don't leave anything, much even salaries. Okay. So anyway, let's take a real quick break. We'll come back and finish up the last two here. I'll put this on pause. Please remind me. Team.
What time is it?
Okay, I know. Yeah. Yeah. Okay. Oh, I forgot to turn on the projector. Okay. We're still talking about minerals. We talked about silicates. We're now talking about the non-silicates. And we'll get the projector up in a minute. I forgot to press the button. We talked about what percentage of the Earth's crust are silicates. 92%. Way. Most of it is silicate. Pick up any rock, sand, anything out there, most of that has silicate in it. Now, if you happen to pick up limestone, most of limestone will be non-silicate. However, there's still, we'll talk about this a little bit later. Okay, the last two things here, this one is not as many, hydroxides. There's, I think goethite is an aluminum hydroxide. That is probably the most common form of aluminum ore, as in bauxite or something like that. So there are a few hydroxides that are out there. That's way down the list. And then after that are your native elements. And someone's already mentioned gold, copper, silver, nickel, the things that just show up as pure elements, okay? Not combined with other things. Now, some copper showing up as natural copper, once it gets to the surface, it'll turn into copper sulfate. I bet you all of you have seen that. It's almost a bright blue. Copper is like a penny, right? Right. But then when it gets exposed to, say, sulfuric acid or vinegar or things like this, it will turn almost a bluish green.
Like the Statue of Liberty.
Say again?
Like the Statue of Liberty.
Yes, exactly. And that's probably why. I don't know. I'm guessing it has copper in it. But yeah.
From copper.
Yeah, and then after a while exposed to the element, it's no longer pure copper. It's now copper sulfate. So, but the native elements are the last of your non-silicates. Okay. Now, here is the diagram that lists them. Okay. Now, this is in your book. You can probably read it far better in your book than you can here. I'm going to have to get awfully close to read it. Your minerals. Now, this looks like they're sort of balanced. Silicates and non-silicates. What are they really? Oh, like this, okay? 92% silicate. This is the common minerals in the Earth's crust. And only 8% non-silicates, okay? Now, among your silicates, they haven't gone into this in great detail yet, but we're going to get there. You have three kinds of silicates. Ferromagnesium silicates. That's iron, magnesium, silicate. Okay? Then you have your non-ferromagnesium silicate. That's anything that doesn't have iron and magnesium in the silicate. And then the clay minerals, which are sort of unusual, and we'll talk about those. Now, actually, I said these were in the crust. A lot of these that are listed here are below the crust. These are ferromagnesium silicates that exist way deeper than the crust. Now, some of these do exist in the crust to some extent. You'll find some, but biotite, you don't need to know these specifically, but one thing about that, okay, y'all know what granite is, right?
Yes.
It's mostly light colored, okay? But you'll always see these little specks that look like black pepper or something in it. That's mostly biotite. That's iron silicates, okay? Ferromagnesium silicate. Hornblende is another mineral. Augite, some of that could be augite too. Olivine, these are getting deeper and deeper, so less likely to be in the granite, but there could be bits of it there, okay? The non-ferromagnesium silicate, and by the way, your ferromagnesium silicate are almost always very dark. The iron that's not oxidized, which would be red or blue, will be very dark, okay? They're also very dense. So when you say the non-ferromagnesium silicates, when they say they're lighter, that means lighter density, but also lighter color. So the light means two things. Quartz, almost clear. Remember those pictures we had of them, very white or clear looking crystals. Muscovite is white mica. That's largely potassium. There's a good source of potassium there. Your feldspars, there's a bunch of those. These are aluminum silicates, not iron, but aluminum silicates, and these are subgroups of feldspars. Okay? There's plagioclase, which is a sodium feldspar. There's another plagioclase, which is calcium feldspar. And then there's orthoclase, which is potassium feldspar. So there's three different cations, sodium, calcium, and potassium, which basically are all on the periodic table in the first two columns. Okay? And the feldspars, they're all aluminum silicates. That's the right-hand side of it. Okay. So those are the non-ferromagnesium silicates. Okay. Now, what are the clay minerals? The clay minerals are silicates that have broken down and then reformulated. But when they reformulated as incredibly tiny little crystals. Okay? When I say incredibly tiny, what makes a clay is the particle size. Here's a dime. Now that dime is about 1 millimeter thick. Okay? And I thought Shalanda was coming back. Okay. I'm here.
Okay.
Oh, you didn't recognize it was me. Okay. If I had two dimes together, that is about 2 millimeters. That would be the largest size dimension of a sand particle. Okay? Do I have two dimes? I don't think so. Yeah, I do. There it is. Two dimes together, that's the largest size of a sand particle. A silt particle, which is another classification, I can't give you an exact size, but sand particles, if you rub them in your fingers, they're gritty. You can feel the grittiness, okay? Get them in your shoe. They hurt, okay? In your sandals, whatever, okay? Silt feels like flour. No grittiness there at all, okay? Okay? Now, clays, take that dime, which is 1 millimeter thick approximately. Imagine this. Slicing that into 1,000 equal slices. Whoa! You are so incredibly tiny there, you'll never see it with your naked eye. You'll never see it with a regular microscope. You have to have an electron microscope to see a clay particle. That's the crystal structure of a clay. It's made when other things decompose and then reform. Very, very tiny little crystals, but they all have a definite crystal structure. Okay, some of the common ones are kaolinite in your pencil lead. Kaolinite is white, okay, but the, I'm going crazy on my words here. We were just talking about it. Carbon in two-dimensional structure, it uses a lubricant. Why is that word on my coop here? But anyway, now kaolinite is the hard part. The dark part is the soot. What do you call that? Goodness gracious. It'll come to me later. But anyway, kaolinite. Now, remember these are very, very small sizes. Now, some of you may be old enough or have been doctored by parents or grandparents who are old enough. When you had a really badly upset stomach, what was... Say that again? No, we're off of that subject now. But you, if your stomach was really upset, they gave you this... Say again? I can't hear, sorry.
Salty and crackers.
Okay, yeah, okay, that was it. But it's a medicine, came in a bottle, you had to shake it up. It was Why? Okay, Pepto-Bismol has it in it.
It was like pasty.
Yeah, very pasty.
Tastes like toothpaste.
You remember what it is? Kaopectate. You've had it? Okay. What makes that good to settle your stomach is those kaolinite crystals are so incredibly tiny, but they're very reactive and they will absorb all that excess stomach acid, stick them to the surface and clog you up maybe, but you would ultimately get rid of it. Okay? That's what kaopectate did. It's a mineral, kaolin. Okay. Illite. Illite is a clay particle made mostly from the muscovite white mica that was your non-ferromagnesium silicate. It broke down and reformed into illite. Chlorite is and there's another distinction among clays. Remember I said they were layered silicates, but they're aluminosilicates. Kaolinite is one layer of silicate. Remember we talked about those sheet silicates paired with an aluminate. Okay, so you have a silicate sheet, aluminate sheet. It's called a 1-to-1 clay. Your illites are a 2-to-1 clay. Silicate, aluminate, silicate. And that's what makes a sort of aluminate sandwich. Okay, that's your illite and other minerals as well. And your chlorite is almost a 2-to-2. Aluminosilicate, aluminosilicate. Okay, so they are 2-to-2 clays. They really expand when they wet. They get water trapped in between. But all clays will do it to some extent, but the chlorites are really bad at it. So those are your silicates. Over on the non-silicate side, which counts for the surface of the earth, only 8% of the crust of the earth. You have these 8 types. They only list 6 here. Which one are they missing? Pretty sure they listed 8 in the earlier slide, didn't they? Oh, hydroxides maybe. Did they leave out hydroxides? Yeah, they left off hydroxides here. Like I said, that was a very small category. Okay? Here are some of the non-silicates. Now, you might say, why do they give so much effort here to them when there's so few of them? But they are important. The carbonates, the main ones, are calcite and dolomite. Now, when we do the next lab, the calcite, I have some very beautiful calcite crystals that were brought to me by a student in this class probably 6-7 years ago. He also was a coal miner. And calcite, I didn't know it, calcite happens along with coal. So, wow. So, I've got some of those crystals. Dolomite is in the calcium carbonate mixed with magnesium carbonate. Next was sulfates. Your major ones there are gypsum, which is calcium sulfate, and hydrate, which I don't remember exactly the chemical formation, but another one is Epsom salts, which is magnesium sulfate. Then your oxides, hematite was one, magnetite's another. Guess what the chemical difference is between hematite and magnetite? Absolutely no chemical difference at all. Chemically, they're identical. Why do they give 2 different names? Now remember, these are both iron-based. Hematite is regular old iron ore. The magnetite is iron ore that is naturally occurring magnetic. It just happened to have formed when it was forming along the Earth's magnetic field lines when they were very strong and they became magnetized. So the only difference in these two, this one's magnetic, that one's not. Okay? Limonite, you'll see that in your lab. I can't remember exactly what it is. And then various aluminum oxides. Okay. I guess the sulfides are next. And the one I was mentioning, iron pyrite, that's fool's gold. There's a sphalerite, I don't know exactly, galena, I think that's going to show up in your lab. And then the chalcopyrite, which you would think had calcium in them, no, it has copper in with the iron pyrites. And then the phosphates, the most common is apatite, APA, not APE, TITE. APE is you're hungry, and APA is the phosphate mineral. Halides, halite is one, and fluorite is another, but there are others that you could put there. And then the native elements. These are fairly rare, that's what makes them very expensive. Gold, silver, copper, diamond, and sulfur. Sulfur is not all that expensive, but pure elemental sulfur is a yellow powder. And again, I asked if there are any gardeners. I didn't get very many responses there. If you're ever trying to acidify your soil, take some elemental sulfur and spread on it, you'll lose that. If you're way too basic, in other words, the pH is way too high, you want to bring the pH down and make it more acidic, spread some elemental sulfur. It'll take care of it really big time. On the other side of it, if your soil is too acid, which happens in the southeast a lot, then you put your carbonates on it, limestone, okay? And that brings up the pH and makes it less acidic. All right. There's your table of silicates and non-silicates. Here are some pictures of some of them. These will be your ferromagnesium silicates. What gives that away? Dark color. Okay? Dark colors here, ferromagnesium silicates. The augite over here, the hornblende here. I can't read this. Yo, I can't see it. Okay, let me see if I can read it here. That's the trouble with wearing these, it's hard to do it. Ferromagnesium augite to the right, hornblende to the left, and biotite. I guess the biotite has to be in the center. I couldn't read it. Boy, that's way too bright. I looked at my eyes again. I thought maybe they'd gone down, so no, my pupils are still like that. All right, those are your. Say again.
I hope you drive home.
Okay.
You have to take you home.
I hope
She
you
said-
drive home safe.
Oh, thank you. Hey, driving's not going to be an issue. It'll be dark by then, and then having my eyes dilated is going to be helpful. I won't need the shades anymore. But right now, the light is just, especially the light off of here and the light that was coming in there, it's getting darker now. Okay, on this side, we have the non-ferromagnesium silicates. Okay? And these are mica. That's these here, I think both of these are. Now, one thing that's characteristic about mica, if you do it carefully enough, you can pull it off in sheets. Okay?
That's Michael.
Mica. In the prairie states, back when the country was just populating, and they built their soddies out there because there wasn't much wood, they just dug up chunks of sod where the grassroots held the soil together, and they made bricks out of those. I mean, literally blocks. They didn't bake them, they just used them. And made big, thick structures, and those are well insulated, okay? But they couldn't, glass was really expensive, and it was all made back east. So what they did, they would find sheets of mica and sort of try to get them to meld together. And you couldn't see through them, but they were what they call translucent. They let light in. You couldn't see out of them very well, but they took the sheets of mica for that. Okay? White and pink orthoclase, that's top and center. Okay? This and this. White orthoclase and pink orthoclase. Maybe that's pink orthoclase too. And quartz. Now, how did I know that was quartz? See that crystal structure? Tetrahedral structure, that point here, there. Here's another one right there. Beautiful, big old quartz crystals, okay? Quartz to the dark colored ferromagnesium silicates here. Ferromagnesium silicates, dark in color and dense, okay? Heavy in density. The non-ferromagnesium silicates, light in color and light in density too. Low weight, low density. Okay. Let's move on to, now, bottom of page 440, starting at the bottom right-hand column, physical properties of minerals. This is basically going to be a lot of what your next lab is, okay? We're going to look at several of these physical properties. The most obvious to look at would be color, but it's not a very useful characterization for identifying minerals, because you can have, and you'll see it, when you look at the colors of some of the minerals you're looking at, you're going to range from pinks to clear to white to yellows to greens to blues to dark. Not a very useful classification scheme. But the obvious thing, they can be influenced by just trace amounts of impurities. Some of the quartz that I'll show you while you're doing the next lab are very pink. Most of them are very clear to whitish, okay? Because the pink ones have trace impurities in them. Now, better than color in identifying things is what they call streak. Now, what you have to do with that is get you your mineral and then find some abrasive that's harder than the mineral is and scrape it off and leave a streak on there. That color, even though the mineral may be pink looking, the streak may be white, or vice versa. The color of the mineral when finely powdered, that's a far better classifier than color alone. It's more consistent than color. Now, I just said something else there, something that's harder than the mineral. So there's another scale, is your hardness scale. This is called Mohs hardness scale. Now, I don't think he was Larry and Curly's friend. This is a different Mohs, okay? Hardness is the resistance to scratching. The harder something is, the harder it is to scratch, okay? Two different kinds of hard there. The Mohs hardness scale uses 10 test minerals with increasing hardness, and they number them 1 to 10, okay? Now, the very softest is talc. And how many of you ladies have ever used talcum powder? Frankly, I've used talcum powder when I've had, some abrasion somewhere. So talc is very, very soft. That's the softest naturally occurring mineral that's given the number 1. Okay? Next up to that is gypsum. Now, this isn't a mineral because it's man-made, but it is the same material. Any one of you ever heard of sheetrock? What's the other name for it? Gypsum board. What it is, it's a sandwich of sort of cardboard on either side, and in the middle is this sort of whitish, grayish looking substance. And if you take your fingernail, you can scratch that very easily. That's gypsum. That's next softest to talc. Then calcite. Now, calcite, you'll see these minerals down there, and you probably can scratch them with your fingernail, but it's going to be very hard to. But that's number 3 on the hardness scale. Then you have fluorite, which I've never run into very frequently. That's number 4. Apatite, remember what apatite was? Your phosphorus mineral, and that's number 5. Oh, I was going to say this, and I'm sorry that Miss Lewis has stepped out, because she probably would appreciate this, but y'all may too. I have a really good friend who is a veterinarian, and he chose to go to Cameroon to practice his veterinary medicine with some of the tribes there. He's a missionary in there, but he's not necessarily a preaching missionary. He's there helping the people. who have animals to keep the animals healthy. And he was telling me one time when they were back in the States for whatever they call it, furlough or whatever they call it, and they came down to see us. He said there was a bush, a naturally occurring scrub bush that grew in Cameroon and I think other portions of Africa that they found out traps phosphorus in big amounts. So, hey, that may be what we do. I think I'm terrible with names. Yeah. Justin was saying when you can't find one thing runs out, you find it somewhere else. Well, this is where it may be a place for phosphorus. We may have to start growing this scrub bush and then grinding it up and using it as mulch and getting our phosphorus fertilizer that way. That's what some of the Africans do. So anyway, that may replace apatite need. Okay, that's number 5. Orthoclase, we saw that was one of the feldspars. That's number 6. Quartz, silicon dioxide, very, very hard. The most, quartz is number 7. Very, very hard. And what common material is made mostly of quartz that you make glass with? Sand. And guess what we use to refinish furniture? Sandpaper. It's very hard, and it will, avoid most other materials. Topaz. Ooh, that's number 8. Very, very hard. Now, some sandpaper that won't work on, say, metal and stuff is actually made out of corundum, which is number 9. There's only one thing harder than that. Diamond. That is the hardest naturally occurring mineral out there. Now, when we bought the house that we currently live in, one of the things in the backyard was a concrete slab that went almost, the yard is pretty wide back there, but then it falls off. But on the flat part back there, it had to have been, I don't know, 75 feet or a long way. It had a huge concrete slab. It went around at least one pecan tree, one walnut tree, and a couple of scrab trees. And we said, why is the concrete slab back there? Okay? And here's the answer we got from the realtor. He said, well, I don't know. One of the neighbors said, I asked that question too, and one of the neighbors said they thought the previous owners had it put there for the children's swing set so they wouldn't get dirty if they fell. And I thought, oh yeah, far better to scrape their skin off their, and tear up their clothes on the rough concrete than for them to get dirty. You sure wouldn't want that. Broken bones are far better than getting dirty. I don't know why it was back there. We had it removed. But I wanted a little end of it kept because I wanted to build a shed because the utility shed that had been there was just rotting away, termites and everything else. So I wanted to put a shed there. So I said, let's leave this part of the slab. I'll put my utility shed there, but let's take the rest of it away. So what he came out with is a saw to cut through that concrete. And not only was it concrete, steel reinforced concrete. How in the world was he going to cut that? A steel blade that was encrusted with diamonds. The steel was not going to cut that concrete and without getting really dull fast. Put diamonds, these very small diamond fragments on that blade, encrust that on there. It would cut through anything. Okay? Hardest material, naturally occurring material known to man. I don't know if we've come up with anything as hard, but we've gotten things close.
So diamond is the hardest substance right now.
Yeah, naturally occurring substance for sure. There may be some other alloys and stuff they've come up with, I don't know.
Right.
But diamond is the hardest. If you take diamond on metal, it'll scratch it. Metal on diamond, it won't. Okay. Now, some common objects are sometimes used for comparisons rather than the actual test material. Here are some examples. Your fingernail is in between gypsum and calcite. So it'll scratch through gypsum, but it won't scratch calcite. This is a 2.5. A copper penny is 3.5. Now the sad news with that is there aren't many copper pennies anymore. Copper is too expensive for pennies, so they use a cheaper metal and just have enough copper to give it the color. But anyway, that would be 3.5 in between calcite and fluorite. So it would scratch calcite, but it wouldn't scratch fluorite. Okay, ordinary glass is either going to be a 5 to a 6. Your pocket knife blade would also be in between a 5 and a 6. Somewhere in there, depends on how hard the metal was. Okay, they don't have much that gets up as hard as quartz, topaz, corundum, or diamond. Okay. I'm sure there's some things, but there's not many. So there's the third, hardness. Color, streak, hardness. Crystal form. Okay? Now that's related to the internal geometric arrangements of the atoms. That's your crystal structures we were talking about. 6 basic groups are already mentioned. Those are your isometric, and your tetrahedral, those that we talked about before. You don't need to know those, but this is crystal form. Now, related to that, I don't know if you've heard this term for that purpose, is cleavage. Does anyone know what a diamond cutter is? Now, not like the thing on the blade that was cutting through the thing. A diamond cutter. He's a professional, or she is. They're the ones who are able to take a raw diamond, in the rough, and get it to shape it just like you want. Diamond's the hardest material out there, but it does have what they call cleavage plane. That's the tendency of minerals to break along smooth planes. And that's what makes a diamond so beautiful. They have all these planes, and then the light refracts through those, make it sparkle. Okay? That's cleavage. Now, kind of the reverse of that is fracture. That's the irregularity in broken surfaces, rather than the regular breakage along smooth planes. That diamond cutter that I mentioned, if he happens to hit that diamond or other precious stone just wrong and it fractures, there went a lot of money out the window, okay? Because now you have to use those fragments and put them on blades to cut through concrete, okay? So fracture is the other side of cleavage. Cleavage is that tendency of minerals to break along smooth planes, like the salt crystals, sugar crystals, all those things. Fracture is the irregularity of the broken structure. Now, back to luster. To me, they should have listed this with color, and they do in your lab. This is the surface sheen, okay? Some things will have almost a liquid-like form. They'll call those vitreous. Oh, here they are. Some will have metallic sheens, pearly sheens, vitreous, meaning water-like sheens, and there's several others. You'll see those when you do the lab. But one of the best physical properties to use to determine what kind of minerals you're dealing with is your density. Density is defined, if you had the first half of the book, it's the ratio of the mass to the volume. Mass to volume ratio. Because any material is best defined by its density. If you have copper, whether it's a penny's worth of copper or a bale of copper wire or the copper for the Statue of Liberty, if you were to take and determine the mass to volume ratio, they're all going to be exactly the same. No iron component will ever have that density. Nothing else will. That is an identifier. Now, an alternative to density is specific gravity. Specific gravity is another ratio. That's the ratio of the mineral density that we had up here to the density of water. Okay? And that gets, what that does is lose the units. This is going to be in grams per cubic meter, kilograms per cubic meter, grams to cubic centimeter. Okay? Whereas specific gravity, you lose the unit because you're dividing it by that of water, which has the same density units. Okay? So if you see units with it, that's density. If you don't see units with it, that's specific gravity. Now, there's two factors that contribute to the density. I've already been talking about density. Remember, the ferromagnesium silicates are much denser than the non-ferromagnesium silicates. One of the reasons is the kind of atoms making them up. The ferromagnesium are iron, mostly. Iron is a very dense material, okay? Whereas the non-ferromagnesium, largely silicon, no iron. That's a very light mineral, okay? So that's one, the kinds of atoms that make up the mineral. But the second is the packing of the atoms. There are some atoms and crystal structures that really jam those atoms into a very small volume, making a higher density. Others are sort of spread out, making a lower density, even though the atoms may be heavier. Okay? Doesn't often happen, but it does. There is one material, now this is a mineral, okay? So I guess you could classify it that way technically. In general, what is denser? A gas or a liquid? A liquid, for sure. What's denser, a liquid or a solid?
Solid.
Solid, almost for sure. There's one material whose solid form is less dense than its liquid form. And you all know it. Say again? Ice. You're absolutely right. Because if you have ice and water, where does the ice go?
To water.
To the top. And the water is at the bottom. That shouldn't be. Why does it be? Okay? Because the water molecules, because of can't remember if I mentioned or not, hydrogen bonding, they stick really, really close together. But when they start getting cold and freezing to get into their crystal structure, they have to get a little further apart. So water gets denser and denser as it gets colder and colder until it reaches about 4 degrees Celsius, which would be maybe 34 degrees Fahrenheit. And then at that point, the molecules start getting further apart to get into the crystal structure. That's why ice floats. Water, one of the most common materials on the surface of this planet, has that really, really unusual, almost unheard of characteristic. If it didn't have that, life as we know it probably wouldn't exist. Because why? Because every time you got into freezing temperatures, your bodies of water would freeze from the bottom up, killing all life in the stuff. The polar ice caps float. South America, Antarctica, they float, allowing animals to live underneath them in the water. If that didn't happen, those animals would be dead because it would freeze from the bottom up. Thank you. Someone came up with a really good idea there. Okay. All right. So there's our physical properties. Now, your lab, which we'll probably have next time, is going to be made up of a list of about 19 minerals. And you will look up on computers. We'll go to a computer lab. This is the only lab we'll do this with. Go to a computer lab. Now, if you have your laptops, you can use those too. We'll go to a computer lab, and then I'll give you a few websites to go to, or at least one, and then you start identifying these physical properties of those 19 minerals. It will be a fairly fun, I think, and fairly quick lab. There's a lot of writing to it, but it goes pretty quickly once you get the hang of it. And while y'all are doing that, I'll have some samples of rocks and minerals for you to look at.
You gonna bring it down?
Say again?
You gonna bring it down?
I can't hear you.
Or diamond?
Are you going to?
Oh, am I going to bring any diamonds? I think my wife took them all. Sorry. Okay. No. No diamonds, no gold, no silver. Okay. Sorry about that, folks. Only cheap minerals. Okay. Calcite. Okay. Now, here are some samples of some physical properties, visual samples. Okay. Here is a piece of gypsum. And here's someone's fingernail. And you see they're scratching it. Gypsum number 2, fingernail 2.5. That's why it's able to scratch the gypsum. Okay? On the other hand, this quartz with a hardness of 7 is so hard that even a metal file cannot scratch it. Even if you take a metal file, you can't scratch it. Diamond, you can scratch it. Quartz on diamond, you'll never scratch. Okay? And there's that tetragonal structure again. You see that point? And the four-sided signature. Characteristic of quartz. Okay. Now, let's get to, that was physical properties of minerals. Let's now get to, and the figure in your book of that quartz crystal is even prettier. And you can see that definite tetragonal structure. Okay? Now, let's see, they have a couple of examples here, and I'm going to have trouble reading them, so let me get this. I think this is okay for now. A 4.08 gram crystal of the mineral augite, which is one of those ferromagnesium minerals, measures 1.43 centimeters long, 0.98 centimeters wide, 0.89 centimeters high. And its cleavage causes it to break in a rectangular solid. What is its specific gravity? Well, what you do, you've given its mass. Let's go back to that. Mass was 4.08 grams. And then you determine the volume, 1.43 centimeters times 0.98 centimeters times 0.89 centimeters. That gives you the volume. I'm sorry?
Where are you getting those numbers?
That's in your book.
Okay.
On page, I don't know how yours is numbered, but 443 in mine.
Okay.
They give you the dimensions of the rectangle, and you multiply those together. That gives you the volume of the mineral. You know its mass, divide the mass by the volume. And they show you how to do it here, and it comes up 3.26, which is pretty common for a ferromagnesium mineral because those are so dense. Okay? Iron is very dense. It's example 17.1, right at the end of section 17.2. Okay. Then they have another one, example 17.2. Again, I can't read it with these on. A 6.39 gram crystal of mineral potassium feldspar. Hey, it's a non-ferromagnesium mineral. It measures 1.82 centimeters long by 1.18 centimeters wide, 1.16 centimeter high. Its cleavage causes it to break in rectangular solids, so you can multiply those three together. What is its specific gravity? 2.56. Okay? So you see the high iron content, 3.26, low iron content, almost zero iron content, 2.56. So big difference in their densities. Okay? Those are two examples that are worthwhile. Okay? They illustrate the densities of ferromagnesium silicates to non-ferromagnesium silicates. All right. So let's go back to mineral forming processes. This is 17.3. Now we're going to talk about some of this a little bit later as well. But the formation of many of the minerals come from two completely different liquid environments. And these are the most common. The first of these, when you think liquid environment, you'll think water solution. For certain, you can get mineral crystals out of water solutions. All right? I don't know if you've ever done this, but you are going to fix you some beans, right? So you put a pot of water on the stove, and you turn on the heat, and you want it to get hot before you put the frozen beans in or the fresh beans in, whatever. And you say, I need some salt in there, so you put, sprinkle a pretty good quantity of salt. But then you get to talking on the phone or watching your soap or whatever, and you forget about putting the beans in and leave it on the hot heat, and you go in, the water is evaporated away, and what's left in the bottom?
The salt.
Crystals of salt.
Mm-hmm.
Now, when you put that salt in there, in that hot water, there weren't any crystals. It all dissolved. But then when you evaporate the water away, the crystal concentration gets higher and higher and higher, and you form new crystals. Sometimes those crystals will be way bigger than the salt you put in there. Okay? So that's water solution. The crystals form from highly concentrated ions in the liquid, and the liquid gradually evaporates away or disappears, gets sucked away or whatever, leaving the crystal structure. Now, I see this happening in another way. If you have any house plants, which doesn't sound like all the gardeners, okay? If you have watered your plants with something, say the water is high calcium content or something like that, and watered the plant, and they're in these clay pots, the water will evaporate away, leaving a white residue. Those are probably calcium carbonate crystals. Very small ones, but that is the crystals form from highly concentrated ions as the water dissolves away. That's one liquid environment. The second one is very different. This is magma. Does anyone know what magma is? Melted rock. You're absolutely right. Molten rock that comes from way deep inside the earth. Remember, the core is actually mostly melted, molten rock. But even portions of the things outside the core are molten rock too. And if this magma ever makes its way to the surface, as it does and cools, then different minerals crystallize out of it. Okay? It can happen below the Earth's surface, or it can happen above the Earth's surface. Magma below the Earth's surface is called magma. When it gets above the Earth's surface, we call it lava. Magma pours out of the Earth's surface into the environment. That's called lava. Now, this can be underwater or in land. Either one, that's called lava. Magma, when it's still inside the Earth, is still just called magma. It can cool enough inside to form some crystals, or it can cool outside. Now, usually when it cools outside in the air or in water, it cools very rapidly. Yeah.
So I recently found out that fresh water is lighter than salt water.
Lighter? Mm-hmm. Yes, of course it is.
I mean, I didn't know that.
Yeah, it is. Because salt water has salt crystals dissolved in it. So that makes it denser, heavier. And any ship that goes both on salt and fresh water will have two water lines. One for fresh water, which it sinks further. Salt water it sits higher. So it actually has two water lines. Yeah, you're absolutely right. Okay. Now, what are the factors that contribute to these mineral forming processes? Here are the important ones. Temperature. Okay? We'll see how this affects. High temperature things that come out of solution there tend to be very high in iron content, very high density, a lot of things with that. Another is pressure. You can have a very high temperature, but with a lot of pressure, it will force something to solidify faster. Low pressure, it may not solidify as fast. So pressure is the other. Temperature for one, pressure for another. Well, this seems strange, but time. The longer it takes for something to crystallize, usually the larger the crystals are. The more rapidly it crystallizes, the smaller the crystals are. Okay? And then the other important factor, remember back here, concentration, highly concentrated ions, the availability and concentration of the ions in the solution. If you don't have many there, it's going to take a lot of effort to get them to solidify. You have a high concentration there, and it happens over a long time, you can get some really big, beautiful crystals out of it. Now, as I said before, when you have lava getting to the surface and cooling very quickly, it may be you don't get crystals forming at all. That's what's happened with the glass. Remember, you heat up and melt the sand, and then cool it really quickly, and it doesn't have time to recrystallize properly, so it becomes what we call a glass. And some of the rapidly cooled materials don't have crystal structure, and they are actually called volcanic glass. Rapidly cooled solid lacking a crystal structure. I've asked this question, I can't remember in this class or not. Is any of you Game of Thrones fans?
I have started.
Yeah. I've never seen the show, but I've read several of the books. Okay? But I've heard the show is very different, and I've heard it's quite good. But this is all fiction, of course, but they did use a real name here. Remember the swords or something they could make that would kill the whites or whatever they called those things? Those were made from obsidian. Obsidian is a glass. It's a volcanic glass that doesn't have a crystal structure. So it makes a very, but I don't know. There's no such thing as whites and those other things that they were killing, but there is such a thing as obsidian. I think we'll see a picture of it coming up here too. So let's look at some of the minerals that are formed at very high temperatures. Typically, these are going to be formed very deep in the earth, because the closer you get to the surface, the more the temperature drops off. Okay? Now, the guy who did a lot with this was named Bowen. So he's a potential vapor topic, or this how he developed this Bowen's reaction series. Lots of things could be gathered here for a paper topic. Okay? Now, this is your silicate crystallization sequence. What things crystallize first and which things crystallize later. The first ones are going to be at the higher temperatures and then cooler and cooler and cooler. The ferromagnesium silicates crystallize at the higher temperatures, really mostly way deep in the Earth's surface. And the minerals crystallizing later are progressively richer in silicon, less rich in iron. Okay? So this is, Bowen contributed this concept. And here's what you see from it. Now there's two sides of this. This side over here is largely the ferromagnesium side. Your olivine is going to crystallize out at very, very high temperatures. It's going to solidify first. Then your augite will. By the way, the olivine is going to be very, very, very dark, very dense. Augite is pretty dark, pretty dense. Hornblende is next, and finally your biotite. It's still dark because it has iron in it, but it's not going to be as dark as olivine, augite, and hornblende. They get progressively lighter in color and lighter in density. Let's go to the non-ferromagnesium silicate side. Now, I don't think these are equivalent temperatures. They drew the scale just to scale it out this way. And if you remember some of these that we were mentioning, these are your feldspars here, okay? Your plagioclase feldspar, I think, is high calcium feldspar. There it is. It's going to come out first. We don't see that much at the surface, but you do find some. Then what comes out next are others moving down to sodium feldspars. So in between here, you have mixtures of calcium and sodium. Calcium comes out first, then you get some calcium with a little sodium, more sodium, less calcium. Finally, your sodium feldspars come out. And then at the bottom down here, you get your potassium feldspar, followed by, I think that says muscovite, but I can't read it. Is that what it says? And, yeah, muscovite. Now again, muscovite is a high potassium, like you see here, but it's almost a layered silicate, okay? And finally, you get quartz, which is your bright, clear crystal, no color in it at all, generally. There may be a little bit, like I said, I have some pink quartz down there, but this is the lowest temperature. Now, it still may be very deep in the earth, but at a lower temperature, and if it goes over time, that's what makes the big, beautiful crystals, those tetragonal crystals. The sand particles, they are quartz crystals, but they're very small. They probably, the time element was very low for them. There's Bowen's reaction series. The lowest iron content, lowest temperature to come out of solution is the quartz, okay? Way at the bottom. All right. Minerals formed at normal temperatures, okay? Not the high temperature ones. Those are usually your ferromagnesium and non-ferromagnesium. Here are the minerals formed at normal temperatures, okay? Those formed at the Earth's surface with contact with oxygen, carbon dioxide, and water. You're going to have water hydrates, carbohydrates, okay? Carbohydrates, sulfates, oxides, halides, sulfides, all non-silicates, okay? Now, except for those oxides here, these typically have lower hardnesses, lower specific gravities than minerals formed at the higher temperatures, okay? The oxides, because some of those will be iron oxides, aluminum, some of those will be hard and have higher specific gravity. But except for them, the others tend to be not as hard and lower specific gravities. Okay? Does that make sense? How are we doing on time?
We have about 2 more minutes.
2 more?
10.
Oh, 10 more. That's much better. Okay. Now, I can't find this in the text here. Okay? They've sort of taken this out. The slide set were from an earlier edition. I don't have the slide set for the current edition. I don't know if they've even come out with it yet. But just a little bit about altered minerals. We're going to talk about this a little bit more in the rock section. Exposure to different environmental pressures, temperatures, and chemical solutions can change minerals into new ones. We'll see that more with the rocks than we will with the minerals, but it can happen. Generally, this occurs at really high temperatures. Now, the boiling point of water is 100 degrees Celsius. So this is another 50 degrees Celsius hotter than that. That's hot, really hot. Look at these pressures. We have above us about 1 atmosphere of pressure. Okay? So that's how much the atmosphere weighs. Okay. Now, if you were to go underwater 10 meters. What's 10 meters? This is 1 meter, here's 2 meters, that's about 3 meters. So a 3-story building, so go to the edge of the building down there, that's 3 stories there. That's close to 10 meters. Now, that's pretty tall. Go down underwater 10 meters, you have another atmospheric pressure. Go down another 10 meters, another 3 stories down, you have another atmosphere. How deep do you have to go to get 2,000 atmospheres of pressure? Okay, that's a mighty tall building. Okay, no, that's way, way below the surface of the earth. Get that kind of pressure and really high temperature. That's when you start altering your minerals and, by the way, altering your rocks. Now, they give some examples of this, but they really don't give a very good thing. They just say examples of altered minerals. Garnet, which, is that a red stone? Or I don't know my semi-precious metals. What color is garnet? Anyone know? Is it red or green? What? Red, okay. I don't even know what epidote or epidote is. It must be a mineral. Talc, remember that's that softest mineral. It's basically been altered some way. Now I have heard something recently that talcum powder has become kind of a no-no.
Right, asbestos.
Asbestos in it? Okay, I didn't know if that was it or not. Graphite, that's what I was trying to think of before. Graphite is an altered mineral, two-dimensional carbon compound. Serpentine is one of those asbestos sources. That's one of those chain silicates that can cause asbestosis and all those bad lung problems. Okay. Don't worry about this too much. That's not even in the text anymore. But we will be seeing some of this show up in the next part. Now, this also doesn't show up here, but it did show up in the table. These are your ore minerals. Okay? Those are in the non-silicates. Okay? That last the mineral elements. Mineral deposits with economic value, often found in veins. These are thin, flat bodies of mineral material, left over from the crystallization of magma or flushed away by hot water solutions or whatever, just like in the coal mines. I didn't know this. When the coal forms, you get calcite forming too. Why? I don't know, but they did. Okay? Examples of this are pyrite, which is iron sulfide, fool's gold, chalcopyrite, which is a sulfide of copper and iron, some of these other ore minerals. I don't know why they list this as a economic value, because pyrite really doesn't have much. It's a joke. Okay, it's fool's gold, but they list them. Again, that's not in your text in this form, but they were listed in a table in another form.
I don't think we're going to finish our 17.
No, we're not. Definitely not. We've basically just got halfway through, okay? We've got through the minerals. 17.4 begins the rocks, okay? And how much time's left?
508.
It's what?
508.
5:08. Okay, so we've got about 7 minutes. Let's at least introduce you to the rocks, okay? Would you like yours on the rock? No, no. Okay. Oh, you're not supposed to. You will. Okay, all right. Now, what is a rock? Okay, it's an aggregation of one or more minerals and perhaps other materials that may not be minerals. Okay, sort of stuck together. Okay, the mineral part are physically combined to make rocks. Okay. And remember when I said limestone was largely calcite, which is calcium carbonate, but it probably also got some silica in it, which is a non, okay. Calcium carbonate is a non-silicate, but quartz is a silicate. So a rock can have mixtures of these things. And sometimes materials that aren't even minerals, like seashells. Or something else, fragments of things in there, bones or something. Those are organic, so they wouldn't be minerals. but they may be embedded in the rocks. Most rocks, because most minerals are silicate minerals, how many percentage? 92% of the surface anyway are silicate minerals. So most rocks are silicate, made up of silicate minerals. Some rocks have some non-silicates in them. That's fine too. Now, there is a classification scheme. We're going to talk about that big time. Based on how these rocks were formed. 3 main groups of rocks. The first is igneous rock.
How you pronounce it again?
Igneous.
Igneous.
Igneous rock. What word do you almost see in there? Ignite, which means fire. So these igneous rocks were rocks that were formed from molten. They were hot rocks that solidified. That's what makes igneous rock. They went from being a liquid to a solid. Those are igneous rocks. Sedimentary rock. What do you think of there? Things that settled out. Okay? Now, I've mentioned the limestone. That's a sedimentary rock.
Sandstone.
Huh?
What about sandstone?
One more. Sandstone? Absolutely. Absolutely. Sedimentary rock.
That's a sedimentary rock.
Yeah,
So, let
sedimentary
me
rock.
understand. The sedimentary rock is layers of
Layers of rock. That's the big giveaway. Is that it comes in layers. Now, sometimes over time, the layers get bent and twisted and stuff so that it doesn't look like layers. Remember that rock we showed at the very beginning? I showed one of the oldest rocks on the surface of the earth. Its layers were all twisted and gnarly, So that's because it undergone, remember that previous slide? Altered pressure, temperature, that's what bent those layers. But they at once were flat sheets later. And then metamorphic. Anyone know what that word means? Second, changing over time? Yes, you got it. Morph means to change. Metamorph means big change. Now, the classic definition of a metamorphosis, does anyone know? Exactly. That hairy little, ugly little caterpillar goes into its chrysalis, or whatever you call that, and comes out a big, beautiful butterfly. That is quite a metamorphosis. I wish I could remember his name. A very famous German writer. I don't think I could stand to read him. I haven't read him, but it sounds like he's really weird. He's a well-known name, but I can't think of it now. He wrote a book, and the title of it is Metamorphosis. His main character in that book was a really obnoxious character. He cheated people, he was ugly to people, he would think, and he woke up one morning as a cockroach. So that was his metamorphosis, and he had to live the life of what he had been being his whole life. That's metamorphosis. I don't know if any of you are into the New Testament much, but if you remember Romans 12:1 and 2, do not be conformed to this world, but be transformed by the renewing of your mind. That transformed is metamorphosis. Be changed big time, okay, by renewing of your mind. Metamorphosis. Okay? Now, do we have time to get going on igneous? 2 minutes? I think igneous can't handle it in 2 minutes. Okay? So we'll begin with igneous rock next time. Okay? And let me get rid of that mark. All right. So let's talk about next time just for a minute, since we have 2 minutes. We'll talk about igneous rocks, then we'll talk about sedimentary rocks, and then we'll talk about metamorphic rocks. And then we'll talk about the rock cycle. That's going to finish the chapter. So I think we can do that easily in 2.5 hours. Okay? We'll probably get started in chapter 18 because I think we'll finish this before 2.5 hours are over with. But then the last 2 hours will be our lab for Chapter 17, which will be the computer lab. I'll find ahead of time a computer lab we can go to, get permission to use it, and we'll go there and do the lab there. Okay? And that will be it for next time. Which means that, yes. Go ahead.
Have you found anything about the trip?
Say that again.
Anything about the trip? Have you found out anything about the trip?
About the
Trip.
You mean the planetarium? Okay, here's what I found out. I called and got a recording that said, none of the scheduled events at the planetarium are happening anymore. We're still looking for an operator. So I thought, boo hiss. But then I found the number of the physics department just to find out from the horse's mouth if that was still true. Or maybe they just hired somebody. So I called there, and they gave me a number. The guy didn't answer, but he said sometimes he may do a special program. So I'm still waiting to hear from him. Hopefully, I called yesterday morning.
We have to ride a bus.
What's that?
We have to ride a bus.
We have to what?
Ride a bus if we go.
Ride a bus? Is that what you said?
Yeah.
I'll try to get the van from the school to carry as many people. Second,
You gonna drive?
I can drive the van. Yeah. Okay, but they don't want to ride with me, huh? Okay, I understand. Okay. But it sounds like it's pretty slim, the possibility, but I'm still going to try. If I can get in touch with them in the morning. I tried yesterday morning, Monday morning, because I have office hours on Monday and Wednesday. I don't have any on Tuesday and Thursday to speak of. So I tried yesterday morning. He didn't seem to be in yet. So I don't know if I can catch him tomorrow morning or not. If not, I may try again Friday.
So we won't have a field trip is what you're saying.
Well, if they're not doing any shows, we can't go there. And the one at Birmingham Southern has been changed to something else, so we don't have another one in the area.
What
So.
about the weather station?
Oh, that's going to come up at the end of the term when we do the weather and climate chapter. That's the next to the last chapter we have. So that'll be at
So
the
that'll
end.
be like beginning of March.
No, end of February. Yeah, end of February. Okay. All right. Any other questions? All right. I'm going to shut this down.